Ryan showed how machine learning contributed to the detection of molecules in space using radio telescopes. He was keen to say that machine learning was only one of the tools they used. He took as his example the creation of that spectacular image of the black hole at the center of our galaxy.
What I was hoping to do with my lecture is to really focus on, so I was prompted to talk about radio interferometry and machine learning, but what I really wanted to focus on was to try to help the students develop an intuition and an idea of what questions they should ask when it comes to the application of machine learning to their problems. One of the foundational advances in astronomy that I presented over the past couple decades was the imaging of the black hole around M87 with the Event Horizon Telescope. And the Event Horizon Telescope is comprised of a number of telescopes across the entire world. So it's a very long baseline interferometer, a VLBI. And what we do is we basically combine those telescopes to create one giant synthesized telescope effectively the size of the Earth. And so the resolving power of those telescopes is proportional to the baseline length. So this is effectively the largest telescope that we can create on the Earth. And we can improve that even further actually by adding space-based components as well. That's something that we're going to try to do in the future. And so with the Event Horizon Telescope, we were finally able to get down to resolving sizes that allow us to look at the gas around a black hole, and we can see effectively the shadow around the black hole. So this was really exciting because it confirmed fundamental physics properties of general relativity, but it's also just cool to be able to see a black hole for the first time. And so what we really wanted to do with this is we knew that the images were going to be very blurry and very hard to analyze because the number of baselines that we have is very low. So in comparison to say something like ALMA, where we have 45 antennas that combine squared to have many baselines, the EHT only has a few baselines. And so the amount of data that we have is very sparse, and it's very hard to reconstruct that back into an image. And so this requires that we fold in a lot of information with prior understanding of what we think things are going to be.
It was really important to make all these different images to show that they all had similar types of structure to them so that we could believe it. Because if you just take one new technique and apply it, maybe that's not particularly believable.
So there's a number of different techniques that we could use to do that, but what we really wanted to do is not use just one of those techniques, but use all of them and then compare their answers and see how confident are we in any particular answer by looking at the ensemble of answers. And so some of those techniques were traditional deconvolution approaches like clean, and others were more machine learning based approaches. So one, for example, was based on this regularized maximum likelihood approach that I presented on in the talk. And so the idea with this is to basically try to create a set of conditioning rules, and these are explicit mathematical conditioning rules to try to improve what the image is going to be. And so we can use that to have a mathematical understanding of what the final image that we got out was. The problem with our galaxy's black hole is that it changes very quickly. All the gas around it is moving and changing very quickly in time, and so we actually have to image that effectively like a movie instead of a still image. And so those computer vision techniques were super powerful for being able to retrieve that movie of our own galaxy's black hole. As we've had new techniques get developed, not just machine learning, but just in general, I think it's very common for students to think of, oh, there's a new hammer, I should use that hammer. It's very attractive, it's new, it's flashy, everybody else is using it. But not every problem is a nail. And so it's really critical to be able to add new tools to your toolbox, but to also understand the inventory of your toolbox and use the right tool for the right problem. Unlike other traditional methods where we have approach that understands both the data but also the rules of physics, the rules of chemistry that we interpret it through, machine learning doesn't know anything about that. It only knows about the data. That's not necessarily a bad thing, but we have to be aware of that and how we use it and when we choose to use those sorts of techniques.